Today's lesson is called Relationships Between Two Numerical Variables, Day 2. It says not all relationships between two numerical variables are linear. There are many situations where the pattern in the scatter plot would best be described by a curve. Two types of functions often used in modeling nonlinear relationships are ones that you've heard of before, quadratic and exponential functions. So in example 1, modeling relationships, it says sometimes the pattern in a scatter plot will look like the graph of a quadratic function with the points falling roughly in the shape of a U that either opens up or down, as in the graph below. It says in other situations, the pattern in the scatter plot might look like the graphs of an exponential functions that are either upward sloping like graph 1 or downward sloping like graph 2. So remember, quadratic has that U shape. It's either going to open up or down. And for exponential, you can either think of it as going up the ramp or coming down the ramp. Okay, so at this time, you are now going to answer the questions just in exercise 1 using the information that we just discussed. Please pause the video, try exercise 1, and then resume the video when you're ready to go over the answers. Okay, so for exercise 1, it says, consider again the 5 scatter plots discussed in the previous lesson. What is the best way to describe the shape of the scatter plot? So here you're either going to be saying linear, quadratic, or exponential. And then if you do say linear, you have to make sure you indicate it as positive or negative, like increasing going up or decreasing coming down. And of course, you still have that option of no association, where the points are so scattered that there's no association that you can find. So scatter plot 1, I drew the general trend line there to see that it's going down and forming what looks closest to a line, so that would be negative linear. For scatter plot 2, we have more of a ramp curved shape, which is exponential, and it is going down, so that would be negative exponential. For scatter plot 3, the points are so scattered that there is no association here. In scatter plot 4, we have a U shape, so that is quadratic. And then for scatter plot 5, we have an increasing pattern looking like a line, so this would be positive linear. Now moving on to exercise 2, it says let's revisit the data on elevation in feet above sea level and mean number of clear days per year. The scatter plot of this data is shown below. The plot also shows a straight line that can be used to model the relationship between elevation and mean number of clear days. So a very piece of important information has been given to us just underneath that. It says the equation of this line, which is the line of best fit, is y equals 83.6 plus 0.008x. This is extremely important to us because we can use that equation of the line to help us make predictions about this situation. So at this time, again, what I would like you to do is pause the video, and you are going to try questions 1 through 4 underneath exercise 2. Once you have done that, please resume the video to go over your answers. Okay, now that you've had a chance to answer questions 1 through 4 under exercise 2, let's go over the answers. So number 1 is really getting at, do you see the general trend? It's a slight trend, but if you do look at that, this is a linear pattern that is increasing. So it says, assuming that the 14 cities used in the scatter plot are representative of cities across the U.S., should you see more clear days per year in Los Angeles, which is near sea level, or in Denver, which is known to be the mile-high city? So in other words, if I look at the picture, as my elevation increases, the number of my clear days also increases. So there will be more clear days in Denver because as elevation increases, the number of clear days also increases. Denver's mile high, which means it has a higher elevation than Los Angeles. Now for questions 2 and 3, it says one of the cities in the data set was Albany, and then number 3 talks about another city, Albuquerque. Both of them are asking you a similar question. So in number 2, they're telling you Albany has an elevation of 275 feet. If you did not know the mean number of clear days for Albany, what would you predict this number to be based on the line that describes the relationship between elevation and mean number of clear days? So you're going to see that I circled the word predict, which means you are going to use the equation. The equation allows you to come up with a prediction. And if we have 275 feet, feet is on the x-axis, so you are going to be replacing x with 275. When you do that in the equation, you'll see my substitution using parentheses, and then you can use your calculator to get your answer. You end up with 85.6, which if you round, because we want to have a full day, you would have to say 86 days. Now, similarly, they had you do the same thing for Albuquerque in number 3. Albuquerque's elevation was 5,311. Again, they wanted you to predict, so you should have been using the equation. And since they gave us feet, again, you are replacing x with 5,311. When you do that, you get about 126.088. And if you round that accordingly, that would be about 126 days. So in number 4, was the prediction of the mean number of clear days based on the line closer to the actual value for Albany or for Albuquerque? And how could you tell this from looking at the scatter plot? So first of all, I wanted to show you the differences. So I underlined Albany with 69 here and our prediction, which was 86. We were about 17 days off. For number 3, Albuquerque, you can see I circled Albuquerque with 167, referred back to our prediction, which was 126, and there we were 41 days off. So we were definitely closer for Albany. And then by looking at the scatter plot, how would we know that? Well, it's going to be based on whether or not the point is close to the line or far from the line. So since we were better on with Albany, our point is going to be closer to the line than our point for Albuquerque because we were more off. So I said the further off it is, the actual data point is further from the line. Now we're going to move on together and look at a couple more examples. So in example 2, you have a quadratic model. It says farmers sometimes use fertilizers to increase crop yield, but often wonder just how much fertilizer they should use. The data shown in the scatter plot below are from a study of the effect of fertilizer on the yield of corn. So, for exercise 5, it says the researchers who conducted this study decided to use a quadratic curve to describe the relationship between yield and amount of fertilizer. Explain why they made this choice. Okay, so let's take a look at this. Quadratic means we have that U shape. And if I take a look at this, to me, this looks like we do have that U shape. We're kind of going up, but then coming back down. So in order to describe that relationship, we want to talk about where it's increasing and then where it starts to decrease to show that it has this upside down U shape. So we're going to say let's take a look. If I take a look at this, we're on an upward swing until we get to about 200, somewhere there in the middle, and then we start coming down. So we're going to say from 0 to 200, and this is kilograms per 10,000 square meters. The amount of crop yield, that's what it's called, crop yield, increases, and after 200, and we'll do kg per 10,000 square meters, the crop yield decreases. So that's how I know it's quadratic. Remember, a quadratic can be U-shaped and open up, or it can be arc-shaped and open down. So this happens to be one that's opening down. Now in number 6, it says the model that the researchers used to describe the relationship was the equation that you see there, y equals 4.7 plus 0.05x minus 0.0001x squared, where x represents the amount of fertilizer and y represents the corn yield, and it has their units next to it. We're going to use this quadratic model to complete the following table, then sketch the graph of this equation on the scatter plot. So I already made a mark up here that I am going to erase. I was just making that mark initially so that you could take a look and see the general shape. We'll go back and make an actual perfected arc after we analyze question 6. Now, if you think back to what we learned about quadratics, the middle of a quadratic, the turning point, okay, is the axis of symmetry, which is the line that cuts that in half. Okay, so we're talking about the line that would cut a parabola that looks like this down the center. So we want to find the axis of symmetry here to make sure we kind of have the correct area for turning point. So we're going to use x equals negative b over 2a. And if you look at our equation, it's going in ascending order, so just be careful here. Your b value is here, 0.05. So we're going to have x equals negative 0.05 from the formula. And then you're supposed to put that over 2 times a. So be careful that you look at the correct a value. Your a value is the number in front of the x squared there. Okay, so that's going to be a negative 0.0001. So if we actually type all of that into our calculator, we would see that our turning point is actually at x equals 250. Now, I know we used 200 up here looking at it, but if we wanted to perfect that now we know it's really increasing really to 250. We'll just kind of put a note of that there now, and also after 250, because now we have more information. So using that information, we're going to actually complete this table, okay? If we go ahead and take a look at what this graph should look like, 250 is about halfway here, right? So you want to make sure that your curve is kind of going up and back down like that, starting to go back down at that axis of symmetry. Now, since we know the x value, if we want to find the y value, you guys should remember that you take this value here, x equals 250, and you put it in for x here, you put it in for x here, and you evaluate what you would get for y, right? So you can do that with all of these x values. You would put 0 into the equation, see where y is. Put 100 into the equation, see where y is, and so on. To speed this up, I'm going to tell you that I've taken all of these numbers and I have already put them into the equation y equals 4.7 plus 0.5x minus 0.001x squared to figure out those for you. If you want to pause the video at this time and practice plugging those in on your calculator and seeing if you get the same responses, you can always do that. So when you plug in 0, which makes sense, if I put a 0 in for x here and a 0 in for x here, you're just going to get 4.7. If you plug in 100, you end up getting 8.7. When you plug in 200 and 300, you get 10.7. And when you plug in 400, you get 8.7. So you're going to see that familiar kind of pattern start to show up where the repeats happen and you see the symmetric part of it. Now, 200 and 300 are both at 10.7 because remember over here on the side when we found the axis of symmetry, we would have 250 and then we would have to plug in 250 to see what's across from it on the other side. Okay, so in number 7, based on this quadratic model, how much fertilizer per 10,000 square meters would you recommend that a farmer use on his cornfields in order to maximize crop yield? Justify your choice. So where are you going to make the most? Well, if I go back up here, remember, you're going to make the most at the very top of this arc where the axis of symmetry and the graph intersect. So that's going to be at fertilizer of 250 kilograms per 10,000 square meters. So we'll say I recommend 250 kilograms per 10,000 square meters of fertilizer because there will be the vertex, well, I should say this will be, sorry. This will be the vertex, so we're going to underline that key vocabulary word here, which in our case is a max because the quadratic is opening down of the quadratic model. So there's an example of a quadratic situation. Lastly, let's look at example 3, which is an exponential model. It says, how do you tell how old a lobster is? This question is important to biologists and to those who regulate lobster trapping. To answer this question, researchers recorded data on the shell length of 27 lobsters that were raised in a laboratory and whose ages were known. So as you can see, before we even start answering questions, you can see an increasing pattern in a ramp type shape, which is why it's an example of an exponential model. Question 8 says the researchers who conducted this study decided to use an exponential curve to describe the relationship between age and exterior shell length. Explain why they made this choice. So what's the overall characteristics of an exponential model? Well, this one is increasing, but not at a constant rate because it's not a straight line. So we're seeing a slow increase to start, and then as it continues to increase, it increases more rapidly towards the bottom, which is why you see that sharp turn that goes upwards much faster than earlier. So that's what we have to explain. So we're going to use that with what we have. So exterior shell length is on your x-axis. As that's going up, your age in years are also going up, but going up at a quicker rate. So we'll say as the exterior shell length increases, so that's the x value, the age of the lobster also increases. Okay, so that helps us with the increasing pattern. But we want to describe why the exponential shape. So we will say the growth is slow at first, then rapidly increases as the lobster gets longer. Okay, and so that's why it curves the way it does and you have an exponential shape. Number 9 says the model that the researchers used to describe the relationship is, and it gives you the equation. And you can tell it's exponential because they have a base of 10, and then in the exponential spot, they have negative 0.403 plus 0.0063x. X represents the exterior shell length, as you know from above, because it's on the x-axis, and Y represents the age of the lobster in years. The exponential curve is shown on the scatter plot below, so I'll show you that in a second. Does this model provide a good description of the relationship between age and exterior shell length? Explain why or why not. So if I scroll down and actually show you the curve that they drew in, I would say that this is an excellent representation. It's hitting some of the points. It's in the center of the data. Most data points seem close to that, and it's definitely showing the slow increase followed by the rapid increase at the end. Okay, so we're going to go back up and answer this question. We'll say this is a good description based on the following shell lengths. And predicted age. So keeping in mind what our actual equation is, we can pick some examples and see if we're on the money, if we're getting the value that we're supposed to be getting. So we're going to go through a couple of them. Let's say when x equals 75. So when x is 75, I'm going to do this once just to show you what you would do. You would take that equation, and then in x's spot, we would put a 75, and that will go directly in your calculator. You would end up getting 1.2 years old. So let's go down and actually look at the diagram, or the scatter plot, I should say, and see if that matches up. So 75 is right here. If I follow that up, we are a little bit above 1 at 1.2, and that definitely fits the model. So I tried out a couple other numbers as well. I did x equals 100, and we should have had millimeters. That's the units. So 100 millimeters. I plugged that into the equation, and I got 1.7 years old. So if I go find 100, and I follow it up, and I go over, I'm just a little bit above 1.5, which would be 1.7. I also did 125. And if you go down, you can see why I'm picking those numbers. That's what the x values are going by. So I picked 125. I plugged it into the equation and into my calculator, and I got 2.4 years old. If I follow up 125 and follow it over, I'm just below 2.5 at 2.4. So if you want to know if something's actually accurate, you can plug these values in and see if you're being represented correctly on the graph. Also look for the things that I talked about before. Is it following the correct shape? Do the points look closest to the line, etc.? Okay, going on now to number 10. Based on this exponential model, what age is a lobster with an exterior shell of 100? So we already did that. We found that up above when we were trying to find out the accuracy. We have to look, though, at the exponential model of 100. So if we go up and look at 100, and I do a little erasing here. Okay, let me retrace that. We see that it looks like it's approximately 1.7 years. Okay, and then lastly, number 11, suppose that trapping regulations require that any lobster with an exterior shell length less than 75 millimeters or more than 150 millimeters must be released. Based on the exponential model, what are the ages of lobsters with exterior shells less than 75 millimeters? And what are the ages of lobsters with exterior shell lengths greater than 150 milliliters? Explain how you arrived at your answer. So we're going to use our chart to take a look at that. So if we're talking about 75 or less, if I look at 75, 75 was just below 1. The next dots are all at 1 or lower, right? So we're going to say when the lobsters are 75 millimeters or less, they are all less than 1 year old. If we look at the other side of that, 150, if I go and look at about 150 and up in this range, I would see that they're all at, if I follow that over, kind of that top spot, we're looking at 3.5 years and older. So we'll say when the lobsters are more than 150 millimeters, they are 3.5 years and older. This is based on the exponential model. Okay, so in summary, remember, a scatter plot can be used to investigate whether or not there's a relationship. You can have linear, quadratic, and exponential. Make sure if you say linear, you say increasing or decreasing. And exponential can also be increasing or decreasing. Quadratic, we don't state that. And models can be used to answer questions about how two variables are related. This concludes your lesson on relationships between two numerical variables, day 2.